All right. So any questions on course structure or anything before we get started? Okay. Good. All clear? If anything's not clear as we go on, please feel free to reach out to me and ask questions. Okay, so this is a class on heat transfer. So we should probably start by talking about heat. What is heat? Well, I've told you what heat is right here, but really think about this for a second. When you think about what heat is, you might think, well, I know what something is when it feels hot or when it feels cold. Like there's sort of a natural intuition of what heat is. But we need to be a little bit more careful. Like it's always relative, right? Whether something is hot or cold is always relative to something else. And why is it relative? It's because heat is actually the movement of energy, right? It's not the state of being like hot. It is the movement of energy from something to another thing. And that movement of energy happens when there's a temperature gradient, when there's a difference in temperature, either locally in a material or between two bodies. All right, so heat is the transfer of energy due to a temperature gradient. What are the mechanisms of heat transfer? Well, you'd say, first of all, we have the three classic mechanisms. You have conduction, radiation, and convection. That's pretty easy. Well, actually, if you think about it, this convection here, right? I didn't put a number 3 there because it's kind of not a separate thing. It's actually just conduction, right? You have a body that's sitting there that's maybe hot. You have fluid moving over that body, and you have heat conducting locally from that body into the fluid, and then the fluid happens to be moving and transporting energy as well. But really, convection is just conduction where the fluid happens to be moving around. So we'll get into, as we start getting into the convection part of the class, we'll actually develop models for conduction in the fluid, right? And you'll see how that plays out. All right, so the first part of the class, I think we'll probably spend about a third-ish of the class talking about conduction. I know some of you are also taking S2364, which is advanced conduction heat transfer. So this part will probably be easy for you. But we'll talk about conduction. So let's get into the definition first. Conduction is energy transfer related to the interactions of microscale energy carriers within a material. Okay, there's a lot of words there, but again, stop and think for a second about what all these mean. So we have energy transfer, we got that part. Interactions of microscale energy carriers within a material. So within a material, first of all, says we're not radiating, right? We have a single body, and there's local heat transfer at the microscale between, say, atoms or molecules in that body, in that material. All right, so we're within a material, and the heat transfer is happening at the microscale, as opposed to radiation where you have, say, two bodies that are far apart and are exchanging via shortwave radiation or long-wave radiation, right? Conduction. So how do we describe conduction, or how do we model conduction usually? Right? Anybody? It's a vague question, but what is, say, the rate equation that we use to model conduction? Anybody? Yes? Yep, exactly. So Fourier's law is what is used to model the rate of heat transfer due to conduction. All right, so that is going to be just as, is it Doran? Yeah, just as Doran said. So we have our Q dot. So that's our nomenclature here. If you ever can't see or it's too small, please let me know. So Q dot, our rate of heat transfer, is equal to minus K times the partial with respect to some direction. Okay, so dt dx. Well, it's actually Q dot double prime. Okay, so let's talk about notation. So dot, it refers to a rate with time. So we have a transfer of energy per unit time. So Q dot. We have double prime, that is per unit area, right? If we ever have a single prime, that's per unit length. Double prime is per unit area. Okay, so we have this rate equation, Q dot double prime minus K. K is conductivity, thermal conductivity, dt dx. It's important to note that this is heat transfer in the x direction, right? We can equivalently write something for heat transfer in the y direction. Q dot y double prime is equal to minus K partial t with respect to y. And same thing for z, right? Q dot double prime z minus K dt dz. All right, so what we effectively have is a Q dot double prime with a gradient, or the del operator, on temperature, right? So it's a diffusion problem, so we model it with this particular equation. I guess the interesting thing to note here is that this is always describing heat transfer in one direction. So if I know the gradient, say I can do a three-dimensional mapping of temperature as a function of space, and at any point I pick and look at the gradient, I can know the heat transfer in, say, x if I just look at the gradient in x, right? It doesn't care what the gradient is in y. When you're just looking at x, you can get the heat transfer in x. And so this is giving you the partial differential, so you're able to calculate the heat transfer in any single direction, regardless of what's happening in the rest of the surface. All right, so that's Fourier's law. So let's talk a little bit more about where Fourier's law comes from. All right, we need to go a little bit deeper than we typically do in 364. Let's kind of understand how Fourier's law arises, because it's not maybe obvious that heat transfer should be proportional to the gradient of temperature. So let's explore that a little bit. All right, so let's start here. So let me just draw a plot. Let me just draw a plot of temperature as a function of position. This will be x position. And let's say that we have some temperature profile, which I'll draw here, and it looks something like this. All right, some temperature profile as a function of position. And I want to zoom in to the very micro scale. So let's imagine that we go down and we can see layers of atoms in this material, whatever the material is. So let's pick some position, and let's make it, say, here in the middle. And I want to understand, so what is heat transfer at this scale? Like, what is physically happening at this scale? So we've zoomed in, we're at this plane, this infinitely thin plane, and we're far enough in that we can actually see atoms to the left and to the right. So let's say that there's, let me just draw a couple more lines here. So let's say we've got the next layer of atoms is sort of at these two positions. Can you see that okay? All right. So my faint dotted gray line says here we are, and we have these two adjacent positions that we're trying to use to help us develop a model of Fourier's law. Let's say the distance here between these layers is called LMS. That is the microscale length, LMS. All right, and we want to know, like I said, we want to use this to develop a model. The first thing we need to do is decide that Fourier's law is valid for what we're doing here. And it turns out that if you want to make sure that Fourier's law is valid, you need to make sure that the distance between interactions, so the distance between this position x and these two next layers, is small enough relative to the body as a whole that you can model this as a continuum, right? So if we want to model it as a continuum, then we need to use something called the Knudsen number, right? And the Knudsen number is defined as, it's called Kn, and Kn is the microscale length, LMS, divided by some characteristic length, which we'll call L characteristic. All right, microscale length again is here. L characteristic might be something like the overall thickness of the material or the length of conduction that you're dealing with. So if it turns out that the distance between interactions at the microscale is sufficiently small relative to the characteristic length that we're trying to model, maybe it's the mathematical domain, then our Knudsen number is really small, right? It's going to be much less than 1. And that's the criteria that we need to use to decide whether this is appropriate. So which circumstances might come up where the Knudsen number is not much less than 1? Any ideas?
The one example I know of is if you have like a PCB and you have thermal interface material, they usually have beads in them. And when you have very small layers of beads, like 3 micron, the the conduction paths are very large compared to the overall thickness of the material.
Yeah, that's a great example. So you have, if everybody understands, you have maybe a very, very small medium, particle medium, and then there's gaps. So if you're trying to model that entire body of filler material using Fourier's law, is probably not appropriate, right? Because it's not a continuum. There's gaps in that material, right? Another example might be if you have a stagnant gas and it's a rarefied gas and you're trying to model conduction through that gas. There's just not a lot of material there, right? There's a big gap between individual molecules, so conduction using Fourier's law is not an appropriate model. Another example might be if you have a crystalline structure that has a really large lattice, right? Large gaps in the lattice. There you need to use maybe specific lattice models as opposed to Fourier's law. So the continuum assumption relies on this this ratio of LMS cell characteristic being much, much less than 1. Okay, if that criteria is satisfied, then we're okay. All right, so let's actually keep moving here. And what we want to do is figure out, I see that there's a temperature gradient here, and I know that there's going to be heat transfer in the positive x direction, right? Q dot and x plus. What is maybe not obvious is there's also actually heat transfer in the negative x direction. There's actually heat transfer across the boundary this way, Q dot in x minus. Well, it turns out that Q dot x plus is usually bigger than Q dot x minus if there's a temperature gradient. So then the net heat transfer is going to be positive in x. All right, so let's look at this little boundary and actually write out some, say, conceptual equations that help us describe it. So let's pick this Q dot in x plus, and let's write out what is it that's actually happening at the microscale. So let's say approximately for Q dot x plus, we're going to say that this is predicted by the number of energy carriers per second times the energy per carrier, right? And that gives us a heat flux, right? Q dot energy carriers per second, energy per carrier. There we have basically a heat flow across that boundary. Let's break this down a little bit further because this is where the model comes from. So again, this is approximately equal to our number of carriers per unit volume now. So let's express it per volume. And then because we're expressing it per volume, we have to multiply by area, the area of the interface, times the velocity of the energy carriers, times the heat capacity of an individual energy carrier, times finally the temperature. Okay, so this is the same equation, we just sort of rewrote it in terms of per unit volume and added a bit more information. All right, let's write this symbolically because I don't want to write the words all the time. So Q dot x plus is approximately equal to number of microscale energy carriers, NMS, times A times V ms times C ms, our specific heat, times T. Okay. So if we're looking at, this is maybe where it starts to get a little bit more nuanced. So we're looking at heat flow. I picked one of these two heat flows to start, Q dot x plus. So we're looking at heat that's flowing, again, from here across this boundary. If we do that, what is the temperature that we are using to make this assessment of Q dot? Where are we making that temperature assessment, let's say? Is it going to be here or here? Too vague. Okay, so it's going to be at this position. Oops. It's going to be at this position here. That is the last place where the energy carriers have interacted with anything. So that's the energy that they are carrying across that boundary. So this T is actually T at what? T at x equals x minus L ms. Right? So this position right here. So that's qx plus. We can do the same thing writing for qx minus. The only difference is going to be that the energy that is carrying across this boundary is coming from interactions here on the right-hand side. Okay, so q dot x minus is approximately equal to n ms a v ms c ms t x equals x plus L ms. All right, so now our net heat flux is going to be q dot equals q dot x plus minus q dot x minus. Right? We're just combining these equations, which is again n ms a velocity ms c ms. Now it's t x equals x minus L ms minus t x equals x plus L ms. All right. So we have this rate equation. Now it's a little hard to see where this relates to Fourier's law, right? Like it's not immediately obvious how we could get this to be true. Q dot double prime equals minus k, say dt dx, right? It sort of is starting to look like it, but it's not quite there. Okay, so let's move on and figure the rest of that out. Here's the equation we just wrote at the top. It's a little small again, sorry. So let's keep moving and figure out how to get to Fourier's law. The first thing is, Fourier's law is in terms of a heat flux per unit area. So we need to figure out how to make Q dot per unit area. Well, that's easy. Let's just divide by the area that is available. Right? And that would be, let's say, Q dot double prime is equal to Q dot over A, right? Which is then approximately equal to N ms V ms C ms T at x minus L ms minus T x plus L ms. Okay, the next step is let's use the definition of a derivative. All right, so now remember back to what, Calc 1, something like that, pre-calc. So the definition of a derivative is dt dx is equal to the limit as dx goes to 0 of the temperature difference, so T at x plus dx minus Tx minus dx divided by the distance, right? So we're using a numerical approximation, basically, to say the difference in temperature over the difference in distance is approximately equal to dt dx as dx goes to 0. So the distance for conduction here, or the distance of those temperatures, is actually 2 dx. Right? As dx goes to 0, this is true. Right? That this statement is true. All right, so let's use that idea to what we've done above that. And we'll say that now our dx is actually LMS. Right? So if LMS is small, then we can approximate this continuum. We can use continuum equations to describe the behavior here. So we'll say if LMS goes to 0, then what is true? So then we say dt dx is equal to the limit as LMS goes to 0. And then let's express this in terms of the temperatures that are involved. So T at x plus LMS minus Tx minus LMS over 2LMS. Okay, now we're starting to get closer, right? We're almost there. We can use this definition to write out the final equation, which is Q dot double prime equals Q dot over A, which equals approximately equals. well, so where does the minus come from? So let's look for a second. Here we have x plus LMS minus x minus LMS, whereas up here we have x minus LMS minus x plus LMS, right? So just by introducing the derivative, the definition of the derivative, the negative sign appears. Right? So now we write this is approximately equal to minus, let's see, what, minus LMS times NMS times VMS times CMS times dt dx. Okay. The LMS here, this one here, where did that come from? Well, we multiply the entire equation by LMS over LMS, right? Multiplying it by 1. That introduces an LMS out front. And then we end up with this equation because there's an LMS. Let's see, there's an LMS over here. Okay.
Should there be a factor 2 in that as well?
Yeah, so I sort of skipped a step, which was maybe not a good idea. What I care about is that I'm developing an approximate model. Okay. So I'm saying this is approximately true. So I'm cheating a little bit. What ends up being important here is the following. I want to say that this is basically my conductivity. But it's not, you can't directly model conductivity as this. It's only proportional to that. So if it's proportional to that, it's also proportional to 2 times that. Okay, so sorry, that's confusing. So K is actually proportional to that term. Ends up not mattering whether 2 is there or not. Okay. So takeaways. 1, this is an approximation. If you're a mathematician, you probably just cried. 2, there are some important observations. So what affects conductivity? Like, what is conductivity? Conductivity is the product of these physical things, right? It's the product of the spacing between microscale interactions. It's the product of the number of microscale energy carriers, the velocity of those carriers, and the energy that they carry with them, right? So that's really the important takeaway here, is that we're saying conductivity is all those things. And normally conductivity is just something that we measure. But if you were a physicist, you might go and start designing materials by tweaking each of these little knobs, right, and getting it to the outcome that you want. Okay? Any other questions on that? Okay. All right, so what we've ended up with here is basically our model of Fourier's law. Or at least we know where it comes from now. So let's look a little bit more at conductivities. This is hard to see. I wish they put a bigger projector in here, but oh well. Okay, so we know that conductivity is related to the microscale properties. But let's maybe look at examples here. So this chart, let's see, zoom in a little. This chart is showing thermal conductivity on a log scale as a function of temperature on a log scale. So stuff down here is like, orders of magnitude less thermally conductive than stuff at the top. And I guess the important thing that I wanted to show here was which materials tend to be at the top, right? Which materials tend to be highly thermally conductive, and why, right? So first thing, let's look at the top. We have high purity copper, right? Well, why is high purity copper a really good thermal conductor? Well, what are the energy carriers that are moving through any material? Any ideas? Electrons. Yep. So electrons are the most important energy carrier, the most effective energy carrier. High purity copper has very little impedance to the movement of electrons, and it has a ton of electrons available to move. Right? So high purity copper, you're going to be transporting heat and electricity very well. Regular old copper here, not quite high purity. It's a little bit worse, but still very effective. you start going down, and what do you notice? Well, you're starting to see things like aluminum alloy, steel, which is an alloy. Stainless is an alloy. At the very bottom, you have things like gases, helium and air, and Teflon, plastic. So as you go down, you start seeing, okay, something like Teflon, there's a lot of, it's a relatively dense material. There's a lot of matter there, but there's not a lot of free electrons. It's a terrible conductor of electricity. There's not a lot of free electrons, so any of the heat transfer that's happening is happening by lattice vibration, something called a phonon. Right? It's a vibration within the lattice that's transporting energy. That's a slow process, right? The properties that factor into conductivity directly, relate to the molecular properties. Okay, that's kind of the main point. So now we should have an understanding of, say, where Fourier's law comes from, what conductivity is, and how you might anticipate that based on the properties of the material. All right, so let's stop. Any questions? I think 10 more minutes. Okay.
Actually, can you have a polymer that's a good conductor of heat?
Probably, well, this is a good question for material scientists. Usually the organic molecules they just don't have a lot of free electrons. Like they're very good at holding onto their electrons. So like carbon-based molecules tend to not, or carbon polymer tend to not. If you have like pure carbon, something like that, then you do. Like graphite is like a great conductor. But you tend to not have any free electrons in those types of materials. Okay.